Well, for question 1 on problem set 4, we have to choose which one of the following is equivalent to this expression. Okay, we're negating a universally quantified statement in which there's a conditional, and we're told that there's only one of these answers correct. The correct answer, let me just jump to the correct answer and then see what's wrong with some of the others, is part C. The not for all becomes an exist, and the negation goes into this part. When you negate a conditional, you end up with the antecedent together with the negation of the consequent. And when you negate a disjunction, the negations filter in and the disjunction becomes a conjunction. So if you follow the rules about, well, they're not rules, I mean, they sort of are rules, but I recommend you not to think of them as in terms of rules, because that's not really getting at what this course is about. But there are certainly patterns of activity that you can get to recognize. Then what happens is universals become exists. You have the truth of the antecedent. In place of an implication or a conditional, you have a conjunction. And then when you negate these guys, the negation applies to each one, and that becomes a conjunction. Okay, but as I just indicated, or just referred to, really what I want you to do is concentrate always on why it is that you get that behavior. Why does this give you px and not that? Why does negating this give you a conjunction there? So it's all about understanding. If you simply learn to apply the rules, you really don't have a useful skill. Okay, computers are good at applying rules. That's what they do. That's all they can do. People can go much beyond that. Okay, what's wrong with some of the others? Well, the first one is just hopeless. I mean, there's just nothing remotely like that. If you got that as your answer, then either you are having a temporary aberration, or you really, really, really haven't got the issue of this. The others, there are reasons why people could go wrong, and the others were put in because there are mistakes that people frequently make. Okay, in the case of this one, the negation is in the wrong place. When you negate a conditional, the negation doesn't come together with this one. The negation should come in front of here and in front of there. So it's just mixing up where the negation comes in. Okay, but otherwise you apply. So it's like applying. You're basically applying the right sort of, let me call it, rule. You're doing the right thing, but you've got one step out. It's like getting a negative sign, a minus sign in the wrong place in an equation. Looking at this one, well, everything went fine except you forgot to change disjunction to conjunction, but everything else was fine. And in the case of this one, you forgot that should be conjunction, and everything else was fine. Okay, so in cases B, D, and E, there was just one thing wrong, and so it's even possible you just did that by a slip. I mean, heaven only knows, you've seen me make slips often enough in the lectures and the tutorials where I write the wrong thing down or whatever. It's we have to keep a lot in our minds when we're doing these things, and frequently what our hand does isn't what we're thinking it's doing, and sometimes what we say isn't what we think we're doing. Mathematics is like that. When you're really focusing on the mathematical concepts and the heart of it, you can make slips with the writing and with the words you use. I do it all the time, and we all do. That's just part of thinking mathematics. It takes a lot of concentration to focus on the mathematics, and the everyday things like writing and using words tend to miss out on that because our mind is focused on the content. Okay, let's go on and look at number 2 now. Well, as in question 1, let me jump first of all straight to the correct answer, and the correct answer is A. This says there are people and there are times at which you can fool those people. So you can fool some of the people some of the time. Remember, existence quantifiers are what we use in mathematics to capture the word some, or at least one. A little bit atypical in terms of what the word some means in everyday language. Okay, and here the way I've expressed it is there is a person and there is a time such that you cannot fool that person at that time. Okay, there's a person and a time such that you cannot fool that person at that time. which is actually equivalent to saying you can't fool all the people all the time. Formally, you could take that part and you could rewrite it as it's not the case that for all x and for all t, fxt. It's not the case that you can fool all the people all of the time. Okay, but I wrote it this way because we're only asking for the equivalence. I'm not saying which is the closest way of capturing it. I'm just saying which is one's equivalence. Okay, let's look at part B. What does this, well, the first part were the same in all of these three. So the distinction is in the second part. So let's see what this one says. Can we express that in English? Well, it's tricky to express in English because of these American Melanoma Foundation type issues. I mean, you could say something like, oh, let's say you can't fool everyone. Let's try something like this, at some time or other. Well, for everyone, it's the case that you can't fool them at some time or other. I mean, really what it's saying is it's not the case for every person. There's a time when you can fool them. Okay, so you can't fool everyone at some time or other. Yeah, that's sort of, I can't think of a way of saying this that really makes, that reads well in English, and yet which really captures this. But hopefully it's clear what the thing means. You know, it's not the case that for every person there's a time when you can fool them. Okay. To me that says the same, but you know, you may interpret that one different because this is one of these things like American Melanoma Foundation. That it's ambiguous, as natural language so often is. Okay. Let's see again. In the case of this one, what does this one say? It's not the case that there is an X and there is a T, so you can fool. This one I think is easy to say in English. Okay. It basically says you can never fool anyone. Okay. It's not, you cannot find a single person and a single time such that you can fool that person at that time. You can never fool anyone. So this one I'm very happy with. Okay, that one really captures it. And the smiley doesn't indicate that I think that's true. It indicates that I think that's a really clean interpretation of what that one means. Okay, let's go on to number 3 now. Well, and number 4 doesn't arise because we've already found something correct. Okay, let's move on to number 3. Well, question 3 asks us whether this is a valid proof or not. And there are 2 parts of that. First of all, to be a valid proof, it has to be logically correct. The reasoning has to be sound. And secondly, it has to succeed in terms of communication. We have to be able to use this proof to convince a reader that it's true or not. Okay? And let me begin by looking at the second aspect, the communication aspect. Now, that's not about writing things down in a particular way. For example, high school teachers often ask students to write proofs down, especially geometry proofs, with 2 columns where you have the claims, the statements in the left-hand column and the reasons in the right-hand column. That's okay, you can do that. But it's worth mentioning, by the way, that no professional mathematician would ever write down a proof like that in geometry or any other part of mathematics. I mean, I think the point of doing it is to emphasize that there are statements to make and reasons to do it. But when it comes down to it, what a proof is it's a story. You're telling a story that explains why something's true. And to be a good proof, it has to be like a good story. It has to have a beginning and a middle and an end. So let's just see if this argument here satisfies the conditions of being a good story which explains why this thing is true, assuming it is a correct proof, okay? So it begins by establishing, this is the beginning. It says we're going to use a standard method, induction. Okay, so we've shown the reader, we've told the reader what kind of method we're going to use. It's a standard method. So the reader is now clued in to what's going to come next. So we've started the story. Then we tell the story. This is the middle. Then there's a conclusion. Well, the conclusion here is actually part of the middle, if you remember how induction works. The conclusion to the proof is this bit. Okay. This is where The denouement of the story comes, if you like. This is where the drums roll and we take a bow. We've proved the result. Okay, so there's a beginning, there's a middle, and there's an end. And there's a narrative to it. You take the reader through the steps that establish the result. Okay, just like any good story. Okay, so this satisfies the requirements of being good from a communication point of view. Now the issue is the reasoning correct? Okay, well, let's see what we've got. Well, this is the beginning case. This is obviously trivial, right? So let's look on to the next part, this is where things usually get tricky. So we begin by making an assumption. We're assuming 2 to the n is bigger than 2n. Okay, that's correct. Okay, let me tick these as I go through. We've done that. Initial step. We make an assumption. Then we do some reasoning. Let me just see if this is correct. It's usually in this kind of step where things go wrong, right? So this is where we have to do a little bit of algebra. Let's see, 2 to the n plus 1. We've basically we've looked at this and said, how can I get 2 to the n plus 1 out of this? Well, I can do it by multiplying by 2. So 2 to the n plus 1 is 2 times 2 to the n. By the induction hypothesis, 2 to the n is bigger than 2n, and the 2 gets carried through, so that follows from the induction hypothesis. That's correct. Notice that we've given the reason why this is true. We've used the induction hypothesis. We've explained it. We have given a reason. We don't have columns with the reasonings in the right-hand side. We've just, in this case, I just put it in parentheses. Okay, so long as it's clear, it doesn't matter how you lay it out. Clarity is what counts, and logical precision, logical correctness are what are important. How you lay it out doesn't matter. I've just laid it out in a narrative fashion, using parentheses. 2 times 2n is 4n, that's correct. 4n is actually equal to 2n plus 2n, and I did that because I can then say, well, 2n is bigger than or equal to 2, since n is greater than or equal to 1. So that's 2n plus 1. So I've got 2 to the n plus 1, and there's a greater than or equal to sitting in here. 2 times n plus 1. And there's a greater than there. So 2 to the n plus 1 is greater than, that's an underline, I haven't made it greater or equal to, that's greater than 2 to the n. So if I follow these through, I've got a greater than, some equals, a greater than or equal to, so that is definitely strictly bigger than that. Okay? And that's the inequality for n plus 1. Having established it, I've helped the reader realise that I've established it by saying that establishes it for n plus 1. Okay? Unfortunately, it's not true. I mean, the reasoning is correct, but the proof is in fact not valid. And the reason it's not valid is because this isn't true. It's not true for n equals 1. 2 to the 1 is not strictly greater than 2. It actually equals 2. Why did I do that? Well, there are so many times in mathematics when a professional, and I mean professionals here, famous professionals in some cases, professionals fairly regularly produce proofs that are false using the method of induction because they think the first step is obviously true and it isn't. So frequently the first step is obviously true that we tend to habituate to thinking, oh, the first step is always easy. Well, that's not always the case. It usually is easy, but it's not always true. So we have to be very careful. This is the kind of mistake that professionals have made. In fact, some years ago, a colleague of mine that I was working with in Germany was working on a proof. It wasn't an induction proof, but it had an initial first step, and then there was some reasoning. And the complicated reasoning was actually several pages long. It really was complicated. And before the professional published it, he asked me, I was working with him, I was a colleague of his at the time, and he says, well, I'll look at this and check that the reasoning's correct. And I read through the proof. It took me several days. It really was a complicated proof. And in the end, I said, yep, this is correct. I've checked every single line. Well, I'd checked every single line except the first line. And in the first line, he said something like, well, the first step is obviously true. Well, it wasn't obviously true. And he went on and published that result, bolstered by the fact I thought it was correct. And then later, someone found the mistake and said, wait a minute, your first step is wrong. So, not only had he made a mistake, but in reading it through, I made the same mistake. We both just read through and assumed something was obviously true when it wasn't. So for an example as simple as this, I'm sure many of you saw that mistake immediately. And so you realised it wasn't valid. The reason I did it this way was because in more complicated situations where you've got quite a bit of stuff here, And maybe it's not something as simple as this to prove. This is a frequent mistake. You've really got to guard against assuming the obvious, because the obvious is sometimes false. In fact, this one is actually false for n equals 1 and n equals 2. Okay? This is false for the first two cases. If you wanted to turn this into a true result, you would have to say for any natural number n greater than 2. You would have to explicitly exclude the cases n equals 1 and n equals 2. Then you get a true result, because the induction then does hold for n equals 3, the first case, and then this argument's true. This argument is correct. It was the first step that's wrong. So you have to be very, very careful about the assumption at the beginning. It's usually straightforward. In this case, it was straightforward. I mean, I rigged it this time in order to demonstrate a point. But in more complicated situations, it's easy to make that mistake. And the reason is we're focusing on the hard part. This is usually the hard part. In this proof, this is certainly the hardest part. And in other proofs, the bit in the middle, the bit between saying it's induction and the first step, and then having the drum roll and taking about the end, the bit in the middle is often very complicated. So do bear in mind that even though it usually is the case that the first step is obviously true, it's not always the case. So you have to be careful about this. This is a domino proof. And if the first domino doesn't fall down, then the whole row of dominoes doesn't fall down. Okay, well, I've made heavy weather of that because it was a point I wanted to really stress. Let's make sure we don't make that mistake again, okay? Let's move on to number 4. Well, as before, with question 3, let's go through first of all and make sure that it has all of the dramatic structures of good storytelling to make it a good proof from a communicative point of view. Okay, so we're going to use a method of induction, so we note that we're using a method of induction, check. We begin by looking at the case n equals 1, check. Give some reasoning. Assume it's true for n, check. Do some reasoning, do some reasoning, do some reasoning, do some reasoning. Conclude and state that we've reached that stage, that we've established the theorem for n plus 1 based on the assumption for n, and having gone from stage n to stage n plus 1, hopefully with the logic correct, we sign off by saying by induction it's true for all n. Or if you want, you can say QED if you like that, quaderat demonstrandum, the old Latin term for finishing a proof, very popular among high school teachers who were teaching Euclidean geometry, which is where I first encountered this phrase. Okay, the second thing then is to see if the logic is correct. The case, we got stuck. Well, I mean, we got misled on the previous one, or the previous proof went wrong because it wasn't true for n equals 1. Let's just check here if it's true. At least I didn't say it's obvious. I've actually gone through and proved it, but let's see if that's correct. If X is a set with exactly one element, then X has two subsets, the empty set and X itself. That's okay. That is actually true. Okay, so that's good reasoning. So if the set has one element, it has 2 to the power 1, which is two subsets, the empty set and the set itself. Okay, by the way, this symbol is not a Greek phi. It's a Scandinavian symbol, which I couldn't pronounce, but well, maybe I could, but I can't remember how to pronounce it. But it's a sort of a capital O with a line through it, sort of like an O with an umlaut in German. But anyway, let's pass on before I embarrass myself with my mispronounced foreign languages. Okay, actually I should have said mispronounced, shouldn't I? Okay, I couldn't even pronounce pronounced. Alrighty, let's move on here. Assume it's true for n, that X be a set of n plus 1 elements. Then we're going to pick an element to be able to use the induction hypothesis. What we're going to do is pick an element, take it out of the set to form a new set Y, to leave me a set with n elements. So I take a set with n plus 1 elements, take one out, gives me a set of n elements. Now I can use the induction hypothesis to say that has 2 to the n subsets. So I'm going to list them. Then I observe that if I take all of those subsets and I throw in that missing element A to each one of them, then I get a new set of subsets of the same length, a new list of subsets. So all of the subsets are the original 2 to the n of subsets of y, together with those sets, each of which has a thrown into it as well. So it's a subset of y to all the subset of y with a. For advanced mathematicians in the audience, I wouldn't need to say that. Because this is a course aimed at people beginning in university level mathematics, I felt that with you as my audience, my students as my audience, it was important to say this. And when I wrote this out, I wrote this out, and when I wrote it out, I was aiming it at you, the students in this course. Some of you with more experience would not have needed that. In fact, some of you with more experience would have been quite satisfied if I'd said, it's obvious that it's true for step n plus 1. Okay, I mean, some of the community TAs, that would have been enough because they would have had enough experience to fill it in. Okay, but by and large, I think this is a good middle ground for many people. And the only issue is that this last step is perhaps a little bit irrelevant for people with some more experience. But this one's true, the proof is valid, and it's got all the tick marks where they need to be. It's logically sound, and it's well laid out. Okay? So we'd give, whoever did this one, we'll give them full marks. No, wait a minute, that was me, wasn't it? Okay, let's move on to question 5. Well, for question 5, once you understand what the question's asking, I think this one just drops out. You simply observe that for any k, the square root of k squared is rational. In fact, the square root of k squared is an integer, a natural number. Okay, for any natural number k, the square root of k squared is rational. Okay, so if you had trouble with this one, it's because you were probably intimidated by all of those arguments about square roots being irrational. And you were probably thinking, oh gosh, there's going to be some difficult proof by contradiction going on. But, there's another lesson to be learned. I mean, I keep saying don't sort of look for templates. Just because this looks like a question to do with irrationality doesn't mean to say it's going to involve some clever proof involving primes and divisibility. Don't get misled by the form of the question. Don't look for templates. Just ask yourself, what's it asking me for? Can I find infinitely many numbers for which the square root of those numbers is rational? Of course you can. Any perfect square has a square root if it's rational. Okay? So it's not that I know that you all know that fact. So if you didn't get this one right, it's because you were, again, been misled by the format. You were being seduced into thinking that the template takes you into an area that it doesn't. Okay? I'll keep repeating this. Don't look for templates. It's not a good idea in mathematics. Not advanced mathematics. Great idea in high school mathematics. It means you can get through 10 questions in 15 minutes. Then very often without thinking. Okay, but in mathematics, in advanced mathematics, it's all about thinking. Okay, question 6. I'm not going to go through this in detail. Let me just observe that if you go through the proof for square root of 3 and replace 3 by p, where p is any prime, and just check that everything works. Okay, I've already gone through the proof of square root of 3 in the last tutorial session. Just go through that, replace 3 by p, and ask yourself, is there anything in that proof for 3 that doesn't work for all primes p? And the answer is no. Okay, so I've told you the answer, but you should go through and check that for yourself. Okay, well that was problem set 4. There's only one more problem set to go and then we're done with the course. How about that? Okay, bye for now.